Transduction, we talked about a range of needs for transduction that happen, right? So going from low to high efficiency. So on the low efficiency side, keep in mind that efficiency is inversely proportional to frequency change. So if you're changing the frequency, which is proportional to the energy, then you're going to have an efficiency challenge there in doing that. We assume here that networking is going to happen at the telco wavelengths, most ubiquitous, lowest loss on the fibers, the large number of lasers and single photon detectors. So this is a great space to be operating in. If you take the frequency of superconducting like aluminum and look at the emission wavelength, you're at 6,000 microns, or 6 centimeters, which is quite large. So there are transducers. Their efficiency is very low today, but there's investment happening, and hopefully those will improve. We need to really see better, much higher fidelities and efficiencies of that transduction to make it useful for networking. And that's why you see like IBM looking at the kind of physical connections as their first step to scaling. Neutral atoms then operate at emission wavelength of 300 to 600 nanometers. Rubidium and strontium are some of the examples used. So this is much closer to optical, which is great, but not exactly the same. So there's some transduction that's needed, right? Likely with a nonlinear crystal or some other element. And so there'll be an efficiency there, and you want to have those efficiencies be very high. And then trapped ions operate at even closer wavelength to the optical spectrum of 1.55 microns. So these examples are barium and ytterbium. So ytterbium's at one micron, basically 1030 nanometers, and barium at 1.8 microns, even closer to optical. And these are what is being worked on by IonQ and Quantinuum, for example. And so those are even closer to the optical wavelength. Transduction is expected to be even more efficient and easier. And then finally, at the top, high efficiency, the photonic. If you are operating at 1.55 microns, then there's no transduction needed, right? And you can actually just either with on-chip waveguides or with fibers, you can couple sizable quantum computer chips to each other and network there. So those are some of the transduction challenges that we have.